Okay, so let's look beyond Earth for a minute. We're talking about humanity's biggest ambition.
Yeah, not just visiting other planets, but actually moving there for good.
Exactly. And our mission today is to sort of cut through the science fiction and get into the reality of it all, the how and the why we're actually seriously planning to become a multiplanetary species.
It's a huge undertaking, but the reasons behind it are, well, they're really solid. At its core, you have that basic human drive, curiosity, exploration.
But it's more than that, too. The stakes are incredibly high.
Oh, for sure.
I mean, beyond finding new resources or pushing technology, which are great, this is really about survival.
The ultimate insurance policy.
Right. If we have a permanent, self-sustaining base somewhere else, a huge catastrophe here on Earth doesn't mean it's the end of the human story.
And this isn't some far-off dream. The plans are being made right now to build bases on the moon and then on Mars. The generation listening to us is probably going to be the one to do it.
But space is, well, it's incredibly hostile to us. So before we talk about where we're going, we have to face some hard facts, the challenges. Let's start with the most obvious one, the air, or the fact there isn't any.
Right, the vacuum of space. You need pressurized habitats, pressurized spacesuits, all the time. If you get even a tiny puncture, the air rushes out and you'd lose consciousness in, seconds.
So building things that can hold air in while also stopping tiny space rocks from hitting them. That must be an incredible engineering problem.
One of the hardest. And even if your habitat is perfectly sealed, your own body starts to rebel because there's no gravity or microgravity.
We've seen this with astronauts, right? Their muscles and bones get weaker.
They get a lot weaker really fast. It's like accelerated aging. Your muscles atrophy, your bone density just plummets.
So that's why they're always exercising.
It's mandatory for survival. They spend up to 2 hours a day strapped to machines to simulate weightlifting. But what's really strange is how the fluids in your body shift.
Shift where?
Upwards. Without gravity pulling them down, fluids move toward your head. It makes your face look puffy, and it can actually put pressure behind your eyes and permanently change your vision.
Wow. Okay, so physical challenges, and then there's the invisible danger, the radiation.
Silent killer,
Yeah.
On Earth, our atmosphere and our magnetic field protect us like this giant shield. But out there, you're completely exposed to solar flares, cosmic rays.
And you can't just line the walls with lead, right?
Oh, you can't. Funnily enough, if you use thick metal, those high-energy particles can hit it and create secondary radiation inside, which is even worse.
So what's the solution?
Right now, the best bet is materials with a lot of hydrogen. So water is a great shield. Or even just burying the habitat under a few feet of moon or Mars dirt, the regolith.
Okay, so protection you have to build yourself. Which brings us to resources. I mean,
Right.
you're millions of miles from the nearest store. You have to recycle everything.
Everything. Total recycling isn't a nice to have, it's the law.
Mm.
The International Space Station recycles about 93% of all its water.
And that water comes from everywhere, doesn't it?
Everywhere. Sweat, shower water, and yes, even urine. It's all filtered through these incredible systems until it's actually purer than most of the tap water you drink on Earth. It's a closed loop. Every molecule matters.
And then there's the mental side. Being stuck in a tiny can with the same few people for months or even years.
That's a huge one. The isolation, the confinement. Mental resilience is just as important as physical fitness. And if someone gets really sick or hurt, there's no ambulance. You rely on doctors on Earth talking you through it over a radio.
Okay, so with that checklist of horrors, how do we even begin? I guess we start close to home. Phase 1, the moon.
The moon is the logical first step. It's kind of a test run. The travel time is short, only about 3 days. If there's an emergency, you can actually get back.
But what's the big reason to build a permanent base there? What makes it worth it?
The game changer was finding resources. We always thought the moon was bone dry, but then we discovered huge amounts of frozen water ice, trapped in deep craters near the poles that never see sunlight.
And that's not just for drinking, is it?
Not at all. That water is the key. It's what we call in situ resource utilization, or ISRU, basically using what you find there.
So you don't have to ship it all from Earth.
Exactly. You can mine the ice for drinking water. Then you can use a process called electrolysis to split the water molecule into hydrogen and oxygen. And what do you get when you combine hydrogen and oxygen?
Rocket fuel.
Rocket fuel. The moon becomes a gas station for deep space. It changes the entire economic model.
And for safety, I hear we'd build underground.
That's the plan. Building underground or covering habitats with lunar soil protects you from radiation and those wild temperature swings. It can go from boiling hot to freezing cold in a single day.
And what about the gravity? That's kind of a fun one. It's only about, what, 17% of Earth's?
Yeah, which means if you weigh 150 pounds here, you'd only weigh about 25 pounds there. You could jump super high. But more importantly for building, you could move really heavy equipment around easily.
But the energy situation sounds tough. You can use solar panels, sure, but a lunar night lasts for 2 Earth weeks.
14 straight days of complete darkness.
Yeah.
Yeah, that means you need massive, incredibly efficient batteries to keep life support running. It's a huge technical hurdle. The moon is basically our proving ground, if we can make it there.
Then we can tackle the big one. Phase 2. The red planet, Mars.
Mars is the ultimate goal. It's the most Earth-like place in our solar system.
It has seasons, right? And the day is almost the same length as ours.
Yep. A Martian day, or a sol, is only about 40 minutes longer. That's a huge psychological plus for a crew living there. Makes it feel a little more like home.
But getting there is.
Yeah.
It's a marathon, not a sprint. We're not talking 3 days anymore.
No, not at all. You have to wait for the planets to align in just the right way, which only happens every 2 years. The trip itself takes between 7 and 9 months.
And once you're there, it's a freezing, dusty world. The atmosphere is mostly carbon dioxide, and it's super thin, so it offers almost no protection.
And the temperatures can drop to minus 80 degrees Fahrenheit. It's incredibly cold. But the scale of the geology is just awe-inspiring.
Like the giant volcano.
Olympus Mons. It's 3 times the height of Mount Everest. And there's a canyon system, Valles Marineris, that's as long as the entire United States is wide.
But the real excitement, the reason we're so focused on Mars, is the water.
Absolutely. Our rovers have found clear evidence, like dried up riverbeds, that liquid water used to flow all over the surface. And we now know there's a lot of water ice just under the soil.
So to make a colony work, we get into the pure engineering of it. We have to make our own water and oxygen.
Back to that ISRU idea. You mine the ice for water. For oxygen, we actually have a machine on Mars right now testing this out. It's called MOXI.
Oh, right, on the Perseverance rover. How does that work?
MOXI basically breathes in the Martian air, which is almost all carbon dioxide, or takes CO2. It heats it up and uses electricity to crack the molecule, splitting off an oxygen atom.
So it's like a little electric tree.
It's exactly like an electric tree. It proves we can pull oxygen right out of the hostile atmosphere and turn it into a resource.
And that water you mined, you can also split that to make rocket fuel for the trip home. It's all about making it self-sufficient.
And speaking of self-sufficient, you can't live on freeze-dried food packs forever. You need to grow things.
But Martian soil is toxic, isn't it?
It is. It has these compounds called perchlorates. So you can't just plant a potato in the ground. You have to use hydroponics.
Growing plants in nutrient-rich water instead of soil.
Precisely. You do it in sealed greenhouses, and you use special LED lights that give the plants the exact colors of light they need to grow. Mostly reds and blues. We've already tested it with things like lettuce, radishes, tomatoes.
And I imagine growing something fresh, something green would be amazing for morale.
Oh, it's a huge mental health boost, a connection to life. For protein, though, we won't be taking cows. It'll likely be things like insect farms or lab-grown meat, much more efficient.
All of this, the life support, the greenhouses, charging rovers, it all needs constant power. And you've got giant dust storms on Mars that can block the sun.
Solar is the go-to when you can use it, but for constant, reliable power, especially through a 2-week lunar night or a Martian dust storm, you need something else.
What's the alternative?
Small, modular nuclear reactors. They provide a ton of steady power day or night and take up way less space than huge solar farms. For a permanent base, they're pretty much non-negotiable.
But launching a nuclear reactor into space, that sounds complicated. And maybe a little risky.
It is. There are big challenges. There's the weight, of course, but the political side is even bigger. International treaties and safety concerns about launch failures are a huge deal. Everyone has to agree that this is just for power, nothing else.
So the engineering challenges and the political ones are all tied together. Okay, let's say we have the power, we have the water. How do we get everything there and actually start building?
Well, the real revolution is in the transport. The reason this is all possible now.
Reusable rocket.
Exactly. Before, a rocket was basically trash after one use. Now, companies are building these huge rockets that can fly to space and then land themselves back on the launch pad.
And that just crushes the cost, right?
It's transformative. It brings the cost of getting things into orbit way, way down. That's what lets you build giant cargo ships that are like space buses, carrying dozens of people and tons of supplies.
And the cargo has to get there first.
Oh, yeah. You send the robots and the building materials way ahead of time. The humans only show up after the basic infrastructure is ready.
And these robots aren't just little rovers. They're the construction crew.
They're essential. They don't need to breathe or sleep, and they can work in the extreme cold and radiation. They'll do all the dangerous, repetitive jobs.
Like what, specifically?
We're talking about robotic arms and huge 3D printers, but they won't be printing with plastic. They'll use the local soil, the regolith, mix it with a polymer, and print the first habitats.
So they're building houses out of dirt.
Basically, yeah. It saves you from having to ship all that heavy material from Earth. You also have drones flying around, mapping the terrain and finding good landing spots. A lot of them will use AI to work on their own because the time delay to send a command from Earth can be up to 20 minutes one way.
This is really building a whole new civilization. Which brings up the big picture stuff. Governance. Who makes the rules on Mars?
That's a huge question. The current space treaties say no country can own the moon or Mars, which is good for preventing conflict.
But those laws are old. They don't really cover private companies.
Right. Who gets the rights to mine for water ice? Or valuable metals on an asteroid? Who enforces the law if a crime is committed? We need to figure all of that out to make sure it's cooperative and peaceful.
And then there's the really long-term future. This is just the beginning.
It really is. Eventually, we could build these huge spinning space stations that create their own artificial gravity. You could live a totally normal life inside one.
And the ultimate dream of actually changing Mars itself.
Terraforming. It's the idea of slowly changing Mars's atmosphere over like hundreds or thousands of years to warm it up, release its trapped water, and create an environment where you could eventually walk outside without a suit.
That's a project for our great-great-great-grandchildren.
It's a true generational mission, something we start now for a future we won't even see.
In the end, this whole push to become multiplanetary, it's not just about the technology. It's about that human spirit of ingenuity. We're turning those little lights in the night sky into actual places we can go.
And you should remember, every single one of these problems we talked about, from shielding against radiation to figuring out how to grow a tomato on Mars, it needs smart people to solve it. It needs students and engineers just like you exploring these ideas right now.
Keep exploring. See you next time.